Hi there. Today we're going to kind of tie energy conservation and momentum conservation together. So first what we're going to do is review how we classify collisions. Then we're going to consider situations in which we can apply both energy conservation and momentum conservation. We'll talk about when to apply each one of those conservation laws. And finally we will do a particular example in which both energy and momentum conservation is applicable. So first, as part of our review of classifying collisions, let's just define this property we call elasticity. So it's a funny little parameter. It doesn't have any units. So it's the ratio of the relative velocities of the two colliding objects after the collision to their relative velocities before the collision. So you can define this as, if you've got two objects, 1 and 2, F here stands for final, I stands for initial. So you take the final velocity of object 2, subtract away from that the final velocity of object 1. Divide that by the initial velocity of object 1 minus the initial velocity of object 2. So you note that the 2 and the 1 are reversed on the top and the bottom, and that is done on purpose. That's the correct definition of elasticity. And we've got a symbol lowercase k for elasticity. Not to be confused with uppercase k, which we sometimes use for kinetic energy. Okay, so here is how we can classify collisions. So we have 4 basic types of collisions. There's the superelastic, which is a bit of a special case, but which you certainly have seen before. There is elastic, inelastic, that's probably what most collisions are, and then there's also the very special case of completely inelastic. So you can classify these types of collisions based only on what happens to the kinetic energy, if you'd like. So in a superelastic collision, you have more kinetic energy in the system afterwards than there is before. Of course, that energy has to come from somewhere, so often it's some kind of explosion in which chemical energy or the stored potential energy in a spring goes into the energy of motion, kinetic energy, after the collision, after the explosion. Then there's elastic collisions, and kinetic energy is conserved in elastic collisions. So you get exactly the same amount of kinetic energy beforehand as afterwards. In an inelastic collision, some kinetic energy is lost. So again, we have to conserve energy, but there's lots of places for energy to go. When two things collide, some things get warmer often, so there's thermal energy there. So kinetic energy can go into thermal energy. Often there's a big noise, so some of the energy goes off in the form of a sound wave. Okay, so there's plenty of places for energy to go to. And then we have a special case of a completely inelastic collision, where first of all there is less kinetic energy in the system afterwards than before, and in addition the objects stick together afterwards. One thing I should absolutely make clear here is that in every single collision, no matter what type it is, in general, momentum is conserved. So in every single one of these 4 types of collision, we conserve momentum. Because there's plenty of places where energy, kinetic energy, can be transformed into all sorts of different types of energy. But there's only one kind of form of momentum here we're talking about. We'll talk about angular momentum later on in the course, but we won't worry about that for now. So we'll talk about linear momentum. Linear momentum beforehand always equals linear momentum afterwards, in general, in a collision. Okay, so we can classify collisions based on solely what the kinetic energy is doing. However, you can also classify them in terms of elasticity. So in many ways, looking at kinetic energy or looking at this elasticity parameter is completely equivalent. Okay, so in a superelastic collision, we have elasticity values bigger than 1. When the elasticity value is equal to 1, it's an elastic collision. When it's in between 0 and 1, bigger than 0, less than 1, it's an inelastic collision. And in the special case, where the objects stick together, the completely inelastic collision, the K is 0. Okay. So let's talk about just some general guidelines for how we analyze collisions. So first of all, whenever you see a collision, the first thing you want to think about is I want to apply momentum conservation to this scenario. Okay? And generally collisions happen in a very small time interval. Okay? So even if there is a net external force, then that net external force does not have much time over which to operate in which to change the system's momentum. And in many cases, there is no net external force. And thus, in that case, momentum is conserved for the system. Okay, so in general, what we mean by applying momentum conservation is we say the total momentum in the system just before the collision is equal to the total momentum in the system just after the collision. Okay, so in general, kinetic energy is not conserved. Okay, so when you have a collision, you generally don't want to assume that the kinetic energy beforehand is equal to the kinetic energy afterwards. As we talked about, there's plenty of places for that plenty of different forms of energy for that kinetic energy to transform into. So if you know that the collision is elastic, then you can say the kinetic energy is the same before and after. But that's the only time you can do that. However, sometimes, right after the collision, something happens, and we can apply energy conservation to that. Or just before the collision, something's going on, and we can apply energy conservation to that scenario. Okay? So as long as you're on the same side of the collision entirely before or entirely afterwards, often energy analysis can be very useful. But for the collision itself, you generally want to stick with momentum conservation, at least start with that. And then maybe energy is conserved, but you have to know that it's elastic to apply energy conservation. Okay, so we'll take a baseball and a basketball. And what you do is you just stick the baseball on top of the basketball, and then you just let everything go and let them drop to the floor. Okay? So they might fall down a meter or so. But if you do it right, if the baseball stays absolutely vertical on top of the baseball can end up being launched much higher than the height from which the balls were dropped. Okay, so that's an interesting kind of situation. So we're going to analyze that. In our analysis, we'll use the fact that a basketball in general, has a mass which is about 3 times the mass of the baseball. That turns out to be a bit of a special case. By the way, often, if you try this yourself, people often generally use basketballs and tennis balls. So if you get hit by a baseball, it's pretty hard, whereas a tennis ball, a little bit softer. So feel free to try it out with a tennis ball if you really do this at home. Okay, so how are we going to explain what we're going to see here? Or if you do this yourself, how do you explain it? And what we're going to do is we'll actually analyze it as a collision, and we'll analyze it as an elastic collision. That's a bit of an approximation, but that's okay. We can get a long way with this method of analysis. So because we know it's an elastic collision, we can apply both momentum conservation and energy conservation. Okay, so just to go over the sequence of events as to what happens. First of all, we start with a baseball on top of a basketball. Now in this picture, I'm actually showing the baseball, that's that little black circle, separated above the basketball. When you actually do it, you generally put the baseball right on top of the basketball. But this will kind of simplify our analysis here. And they're going to fall to the floor, dropping through a height we'll call h. Okay, so of course, as they go down toward the floor, they both pick up speed. And then the basketball collides with the floor. Okay, so next, what we're going to do is we're going to look at the collision the basketball has with the floor. And we're going to assume it's an elastic collision. And so all this does is it reverses the direction of the basketball's velocity. So the basketball comes in with a speed v just before it hits the floor, and then as it's coming off the floor, it also has that same speed v. Okay? And then the baseball is coming down at speed v, the basketball is going up at speed v. They're going to run into each other. So there's a second collision here. And after this collision, the baseball acquires quite a significant speed, and that shoots it much higher up into the air than it started from. Okay, so we're going to analyze all this situation and figure out exactly how fast the baseball is going and how far up it's going to shoot. Okay, so when you really do it, these two collisions, the basketball floor collision and the basketball baseball collision, basically happen simultaneously. But we're going to analyze them as two separate events just to keep life simple. Okay, it really doesn't change the outcome. Okay, it just makes it easier for us to keep track of what's going on. Okay, so let's analyze just the downward drop. Okay, so this is before any collisions have happened. And here we can apply energy conservation. Okay, so they both go through the same height h, at least up until this picture is happening. And if the baseball is right on top of the basketball, then they definitely drop through the same height h. Okay, so they're both going to speed v when the basketball hits the ground here. So if you apply energy conservation to this, you can say, well, they're dropped from rest, so all the initial energy is potential, gravitational potential energy, and just before impact with the ground, the basketball's impact with the ground, that is, then we've transformed that potential energy into kinetic energy. Okay, so it doesn't matter what mass you have, the masses cancel out in our energy equation. Initial potential energy goes into final kinetic energy. And then we've got a v there, right? We can solve that equation for v. So v ends up being square root 2gh, actually. And then the basketball's velocity after the collision is the same v, just directed up instead of down. So that's what our assumption is about how the basketball floor collision works out. The basketball just reverses direction. Okay, now if that were entirely true, then if you drop a basketball on a floor, it would come back to exactly the same height from which you let it go. Now, if you've ever done that, you know that doesn't happen. So we're making a bit of an approximation here, but that's okay. Let's keep going with it. Okay? And again, we do this basketball floor collision as if it happens before the basketball baseball collision. Okay, so don't worry about the fact that they basically happen simultaneously. Okay, we're keeping our life simple by splitting them up. Okay, so now we've got the baseball and the basketball both with a speed v, and we've got the basketball now going up and the baseball coming down. Okay, so now there's a collision between the basketball and the baseball. Okay, and the basketball, remember, has a mass which is 3 times bigger than that of the baseball. So we're going to give the baseball mass m. We're going to just call it m, and therefore the basketball's mass is 3m. Okay, so this is a collision, so we can say, hey, let's apply momentum conservation to this. The other thing to do is, if you actually see this happen, particularly in the case of the baseball and the basketball, if you look at what the basketball does after this collision with the baseball, then what you see is that the basketball is essentially at rest. Okay, so after this collision, you know the final velocity of the basketball is 0. So we could make use of that if you wanted to. Okay, so this we'll do that first, and then we'll do a better analysis where we don't make that assumption. But okay, let's just use our observational skills and do it. Okay. So if we put this in, the fact that the basketball's collision velocity after the collision is 0, it simplifies our momentum conservation. It simplifies our equation. Yeah, because we only have one unknown, the velocity of the baseball after the collision. So when we say apply momentum conservation, this is what we mean. We mean write down an equation where on the left-hand side you're keeping track of the momentum in the system before the collision. Okay, so up here is positive. So the basketball is traveling at v up, and it's got a mass of 3m. So its total momentum is 3mv in the positive direction. The baseball, mass m, velocity v down, has a momentum of negative mv. The negative sign indicates the momentum is directed down. Okay, if we put in the fact that the basketball's velocity after the collision is 0, then we get just the baseball moving after the collision, so it's got a mass m and some unknown velocity v final. Okay, so on the left-hand side, you got a total of plus 2mv. You got mvf on the right-hand side, so you got to conclude that VF is plus 2V. So in other words, the baseball after the collision is A, going up, and B, got twice the speed it has just before the collision. And if you work it out, you'll find that this solution also does conserve kinetic energy. Okay, so that may be a little unsatisfying to you because we kind of put in this assumption that the basketball is at rest. So let's go back and we'll do a better job of this. Okay, so we will do our conservation momentum equation, but we'll put in an unknown capital VF to represent the velocity of the basketball after the collision. So now our equation is exactly what we had before on the left-hand side. Basketball plus 3 mv worth of momentum, the baseball minus mv. Afterwards, basketball 3 mvf, unknown, and the baseball mvf. So you note that all the m's will cancel from your equation. So you can reduce that down to plus 2v is 3vf, 3 capital VF, that's the basketball's final velocity, plus vf, little vf, that's the baseball's final velocity. So now we have one equation and two unknowns. You can't solve that, so you got to use something else. Okay, so you could do energy conservation here, kinetic energy conservation, but actually it's a lot easier to do the elasticity. So here's our general elasticity equation. K is V2F minus V1F over V1I minus V2I. Okay, so we're going to call the basketball object 1 and the baseball object 2. We know it's an elastic collision. By definition, our elasticity parameter K is equal to 1 for an elastic collision. Okay, so we've got V2F, that's the baseball's final velocity, so we'll call that capital VF. Lowercase vf. V1F is the basketball's final velocity, so we've got our minus sign from our basic K equation, and we put in capital VF, that's the basketball. Beforehand, V1I. V1I, that's the basketball's initial velocity, that's positive V. V2I, the baseball's initial velocity just before the collision. I really should say the baseball's velocity just before the collision. Okay, so then it is minus V because it's going down. So we get V, basketball's velocity, minus V, which is the baseball's velocity. So we get VF minus big VF over 2V, which you can rearrange to. Plus 2V equals minus VF plus VF, and we'll call that equation 2. So now we just got to do some algebra to solve these equations. Now you might even be able to recognize in your head. Plus 2v is 3vf plus little vf, plus 2v is minus vf plus little vf. The only way to make that work is for big vf to be 0. The only thing that makes any sense. So that's what in fact comes out of solving that equation. So big vf works out to 0, little vf works out to plus 2v. Okay. So now we want to know how high this baseball goes. Okay, so remember it came down from a height h and acquired a speed v. Now, at ground level, basically, it's got a speed of 2v directed up. So clearly it's going to go higher than it started from. But how much higher? Okay, so remember we did an energy analysis to relate h to v. Okay, we said mgh is 1/2 mv squared. Now, we've got a velocity of 2v directed up. So we can use exactly the same energy equation. We'll say the initial kinetic energy it has, or the kinetic energy it has right after the collision, which is 1/2 m 2v all squared, is going to turn into ultimately the mg capital H that the baseball has at its highest point. Okay. Now how does capital H compare to little h? Well, if you look at what's going on the right-hand side of these two equations, in one case we have 1/2 mv squared. The other case we have 1/2 m 2v all squared. Well, when you square 2v, you get a factor of 4v squared. So the right-hand side goes up by a factor of 4, which means the left-hand side goes up by a factor of 4. So capital H has to be 4 times little h. So the baseball shoots up 4 times as high as the height from which you dropped the baseball on top of the basketball. Okay, it's kind of an amazing experiment. If you've never seen it, try it out. And like I said, you might want to use a tennis ball instead of a baseball. just because it's hard to drop it so that the ball on top shoots up directly vertical afterwards. So you can get like hit by this ball if you drop it just the wrong way. So be careful of that. The other thing that's kind of neat is if you use a combination of objects where the top object has a mass which is way smaller than the bottom objects, it can even go as high as 9 times as high as you drop it from. Okay, so that's a pretty cool thing to keep in mind too. Okay, so that is a good example of how we use momentum conservation to analyze a collision. Plus, note that in particular on this screen here, we've got energy conservation near the top of the screen applied to the situation before the collision. We've got MGH, initial potential energy, then that transforms into kinetic energy. That's entirely before the collision. Down below, further down the screen, mg capital H is 1/2 m times 2v all squared. That's kinetic energy applied to the situation entirely after the collision. Okay, so energy can be very useful to us either before and or after the collision. Now, of course, in this analysis, we also did energy conservation to analyze the collision itself because it was an elastic collision. But that you don't always do that, only in an elastic collision situation. And in fact, we really didn't do kinetic energy there. We did elasticity instead, which is actually a lot easier. Okay, so that is all for today.